Students, a positive attitude causes a chain reaction of positive thoughts, events, and outcomes. It is a catalyst and it definitely sparks, ignites extraordinary results. So, students, always have that positive approach towards your life.
Jai Hind students, welcome to my YouTube channel, and this is the second lecture of Refraction of Light. So in the previous lecture we have discussed regarding refraction, regarding refractive index, isn't it? We have discussed various terms and terminologies. Here we will start with refracting surfaces. So we are talking about spherical refracting surfaces. Now look, we'll start with convex. We'll start with convex refracting surface. Convex refracting spherical surface. Look, this is a transparent refracting medium made up of glass. Now suppose one of its faces is curved. That is, it forms a part of a sphere. It's like this, suppose. It is like this. So, this type of refracting spherical surface, whose convex portion is towards the rarer medium, is known as convex refracting spherical surface. This is student air, which obviously will act as the rarer medium, and this is glass, transparent glass, which obviously will act as a denser medium. Now look, this curved surface, it's a part of a sphere. It's a part of a sphere. Right? It's a part of a sphere. The center of this would be somewhere over here. Isn't it? So, this bulging part, this is the convex portion, which is towards the rarer medium. So, there are two types of refracting spherical surface. First and foremost, we are talking about convex refracting spherical surface. So, it is that type of refracting spherical surface where the curved surface, obviously it is forming a part of a sphere, and its convex portion, this one is the convex portion, this is the convex portion, and its convex portion is towards the rarer medium. The convex portion is towards the rarer medium. Right? So, such a refracting surface whose convex portion is towards the rarer medium is known as convex refracting spherical surface. Right? Second one, concave refracting spherical surface. Concave refracting spherical surface. Now look, this is also a transparent refracting medium, like this is made up of glass. So obviously it will act as a denser medium. And this is suppose air, which obviously acts as a rarer medium. In this case, the concave portion is towards the rarer medium. This is the curved surface. Okay, like this. This is the curved portion, which is the concave portion. This is the concave portion. And this curved part, it's a part of a sphere, like this. It's a part of a sphere, whose center of curvature will be somewhere over here. Right? So basically, this transparent refracting medium, whose curved surface forms a part of a sphere, is known as a spherical refracting spherical surface. And if it happens that the concave portion is towards the rarer medium, here the concave portion is towards the rarer medium, then it is known as concave refracting spherical surface. So students, any transparent refracting medium having curved surface, that may be termed as a spherical refracting surface. Now spherical refracting surfaces are of two types, convex and concave. So what's the basic difference? In the case of convex, the convex portion is towards the rarer medium, and in the case of concave, the concave portion is towards the rarer medium. Another very important difference, here in the case of convex refracting spherical surface, the center of the curvature will lie in the denser medium. Here the center lies in the denser medium. While in the case of concave refracting spherical surface, the center lies in the rarer medium. So students, these are two basic differences in the concave and convex refracting spherical surfaces, right? And with the help of two convex refracting spherical surface, a convex lens is prepared. While with the help of two concave refracting spherical surface, a biconcave lens is prepared. I'll tell you how and how it is prepared. Look, this is a convex. This one is again a convex. This one. Like this. This is glass. So it will act as a denser medium, right? And its convex portion is also towards the rarer medium, towards air. So these two are convex refracting spherical surfaces, right? Now what we'll do is, suppose we consider these two portions. This is the first portion, this is the second portion. Both the portions are of convex refracting spherical surfaces. Now students, if we join these two, what will be the shape like? It will be like this. This one would be for the first portion, and this is the second portion. If you combine them, it will be like this. Right? So, this is it. This one. And second portion. I am representing it by dots. So, this becomes a lens. Which type of lens? Convex lens. And how it is prepared? By making use of two convex refracting spherical surfaces. So this is, student, a convex lens. It is a convex lens. And we'll discuss further, the convex lens is also known as a converging lens. So again I repeat, students, convex lens is made by two convex refracting spherical surfaces. And a convex lens is thick at the center, while it is thin at the edges. At the edges you can see, these are the edges. At the edges it is quite thin, but at the center it is quite thick. Understood? So this is convex lens. And as I told you, we will verify the fact that convex lens is also known as a converging lens. Now let's come over here. Like this is a concave portion. Let's consider another concave refracting spherical surface. It's like this. This is another concave refracting spherical surface. The concave refracting spherical surface means the concave portion should be towards the rarer medium. The concave portion should be towards the rarer medium. Right? So, this is the first portion and consider this to be the second portion. Consider this to be the first portion, this to be the second portion. Let it be represented by slanting lines and let this be represented by dotted lines. So, both these are the concave refracting spherical surfaces. Now, if you join these two portions 1 and 2, what will be the shape obtained? It will be like this. This is for the first portion. This is for the first portion. And second one, if you join it, this will be the second portion of the convex refracting medium. So student, this combination is made up of two concave refracting spherical surfaces. So this is known as a concave lens. And concave lens is also known as a diverging lens. This also we'll discuss. So basically students, this is convex lens and this is concave lens. Concave lens is formed by using two concave refracting spherical surfaces. So concave lens is thin at the center, while at the edge it is quite thick. So what's the basic difference between these two? Just by touching their surfaces, you can identify easily which lens is concave and which lens is convex. Just by touching its surface. If at the center the thickness is large, while at the edge the thickness is very small, then it must be a convex lens. Otherwise, if at the edge the thickness is large and at the center it is small, and again at the edge it is large, then it must be the case of a concave lens. So I hope students it's obviously clear. It is actually known as biconvex lens. Biconvex, made up of two convex refracting spherical surfaces. It is also known as biconcave lens, actually made up of two concave refracting spherical surfaces. Right? So we have discussed these terms: convex refracting spherical surface, concave refracting spherical surface, and then convex and concave lens. Right? Now let's discuss some other types of lenses as well. So there are some other various types of lenses, but in your syllabus we'll be concentrating and restricting ourselves only to biconcave and biconvex lenses, right? Which we have just now discussed. There are some other lenses as well which we can discuss right now, just the intro part. So there are some other types of lenses as well, like this lens. It's known as Plano convex lens. The surface is planar and this one is convex, so it can be termed as Plano convex lens. Then this one, Plano concave lens. This is Plano concave lens, right? Now this one, suppose we consider this portion and this is the convex portion. Look, this is the concave portion and this one is the convex portion. So this is concavo-convex lens. It is a concavo-convex lens. Then you can consider this as well. This is a convex portion and this one is the concave portion. It is convexo-concave lens. So what I mean to say is that there are various types of lenses which can be obtained by various combinations, right? But in your syllabus, we will be chiefly concentrating only on biconcave and biconvex lenses, right? So these are various types of lenses: plano-convex, plano-concave, concavo-convex, convex-concavo lens. So now let's discuss some terms and definitions. We'll be discussing some terms like optical center, radius of curvature, center of curvature, principal focus, right? Then we'll also discuss why convex lens is known as a converging lens and a concave lens is also known as a diverging lens. So let's first discuss some terms and definitions. So let us discuss both the cases. This is a biconvex lens, right? This is a biconvex lens. This center, imaginary center, is known as the optical center. This is a concave lens. This is a concave lens, and this point O may be termed as an optical center. Optical center is that point inside the lens through which light on passing through that point remain undeviated. So student, remember, first is optical center. Optical center. It is a point which lies inside the lens. It is a point which lies inside the lens and through which, if the ray passes, if the light passes through that point, it will remain undeviated. It won't suffer any sort of deviation in its path. It will remain undeviated. So that's optical center for you, right? Now look, it is made up of two spherical refracting surfaces, both the lenses. Now concentrate over here. Now let's discuss this one. It's a curved surface, we are aware of it. It is a convex refracting surface and it's a part of a sphere. It's a part of a sphere. It's a part of a sphere whose center would be somewhere over here. Let us consider it to be C1. This is for the first one. And this is second. Second surface is also curved. It's also a part of a sphere. It is also a part of a sphere. So its center would also lie somewhere over here. Suppose this is C2. So if both are having the same radius, OC1 is equal to OC2 is equal to R, say. Let us consider the curved surface. Both have the same radius. Then C is known as the center of curvature and its distance from optical center can be considered to be the radius of curvature. Actually, its distance is to be measured from this point and C2 is to be measured from this point. But for all practical considerations, we'll consider the lens to be very, very thin. So this point P1, this point P2 and point O all may be considered to be coincident. All are infinitesimally close to each other. So again I repeat, students, what are C1, C2? These are the center of curvature. So how do you define the center of curvature? It is the center of the sphere of which the curved surface of the lens forms a part. Again I repeat, C1, C2 are the center of curvature. Center of curvature. C1 and C2. There are two centers of curvature. Optical center it was denoted by point O, right? So again I must repeat. Consider this case and then we'll come back to the definition. This is a curved surface, considered to be first one, right? It's a part of a sphere, obviously. It's a part of a sphere. You need not to draw the entire sphere, but logically its center would be somewhere over here. This is the first center of curvature. Again, it has got two curved surfaces. Let's consider the second one. It's also a part of a sphere, isn't it? It is also a part of a sphere whose center will lie somewhere over here. So students, this C1, C2, they are known as center of curvature. So how do you define center of curvature? C1, C2 are the center of curvature, which may be defined as the point, or rather the center of the imaginary sphere of which the curved surface of the lens forms a part. So that is how center of curvature is defined. Now students, radius of curvature. In order to define radius of curvature, first we need to understand the assumption. The lens is considered to be very thin. Suppose this is P1 and this point is P2. The lens is very thin means the points P1O, P2, P1O, P2, they are lying infinitesimally close to each other. So distance P1, C1 may be approximately written as OC1. Distance P2, C2 may be approximately written as OC2, isn't it? So all the distances will assume are to be measured from the optical center. So here, instead of taking this distance P1, C1, we can write it as OC1, which is radius of curvature. Similarly, P2, C2, approximately is OC2, which is equivalent to R, which is radius of curvature. Right? So how do you define radius of curvature? First definition, the radius of the imaginary sphere of which the curved surface of a lens forms a part, that is known as radius of curvature. Or the second definition, the distance between the optical center and the center of curvature, that is known as the radius of curvature. So third one we have discussed is radius of curvature, right? It's denoted by R. Next, principal axis. The line joining C1 and C2. Now the lenses has got two center of curvature, C1, C2, right? The line joining C1, C2, that is known as principal axis. So this is the principal axis. This is the principal axis. So line joining C1, C2 is known as the principal axis. Fifth one, that's aperture. This is basically the size or the diameter of the lens. This is the diameter. This AB, it can be considered to be the aperture. Over here, it's like this. This is the diameter or the size of the lens. That is known as an aperture. So students, these are the definitions which we need to be aware of. Right? There's another very, very important definition, and that's principal focus. That we'll discuss. Right? Principal focus means, as we have studied in reflection, in case of mirrors as well. Now when a parallel beam of light is incident over here, then convex lens will tend to converge the refracted rays. While in this case, the refracted rays will get diverged. It will appear to be coming from a particular point on the principal axis. So that particular point on the principal axis, at which the rays either converge or appears to diverge, that particular point is known as the principal focus. So that also we'll discuss. But I hope these definitions are very clear. I mean, it should be crystal clear. There shouldn't be any sort of problem. Okay, now let's discuss principal focus. And while dealing with this definition, I'll also try to convince you why convex lens is known as a converging lens and concave lens is also known as a diverging lens. So let's discuss principal focus and concentrate on the converging and diverging nature. Okay, this is the convex lens. Suppose let's consider the first case, convex lens. The lens should be thin. The lens should be thin. Student, this is the optical center, right? This is the first surface and this is the second one. It's a part of a sphere whose center would be somewhere over here. Put it as C1. This is another curved surface. It's also a part of a huge sphere. Its center would be somewhere over here. C2, suppose. And we are dealing with the case where both the surfaces have got the same radius of curvature. So OC1 is equal to OC2. Now line joining C1, C2, that's the principal axis. This is the principal axis, right? And this is the reference line. This is the reference line. Now students, actually what happens is, when a ray of light is incident over here, then it will get refracted. Ray traveling from rarer to denser. It will bend towards the normal. Again, it will suffer refraction at the second surface as well. And in that case, it will travel from denser to rarer. It will bend away from the normal. So actually, refraction takes twice at the two surfaces of the lens. But since the lens is considered very thin, therefore, just for convenience, we will show the bending of light from this particular line. Actually, this will happen. If you draw an enlarged view, it will be like this. Look, suppose this is the point where we are dealing with refraction. So, suppose this is the ray incident over here. You can draw a normal over here. So, ray traveling from rarer to denser, it will bend towards the normal, like this. So, this is the first point where the refraction or bending of light is taking place. Here again, you can draw a normal, and here the rays start from denser to rarer. So, it will bend away from the normal. So, it will be like this. So actually, refraction of light takes place twice on the two surfaces of the lens, both in convex as well as in concave. But since the lens is considered to be thin, so just for convenience, instead of showing the refraction twice, we simply draw a reference line and we'll show the bending of light from this particular point, from this line. Is it clear? Okay. Now what to do is, suppose a parallel beam of light is incident. And they are parallel to each other and parallel to the principal axis. These are the parallel beam of light. Like this. And you are aware, optical center is that point through which if the light passes, it will remain undeviated. So look, this is the light passing through the optical center, it will remain undeviated. It will remain undeviated. Now as I told you, I will show the bending from this particular line. Right? Now what happens is, in the case of convex lens, when rays parallel to the principal axis are incident on the lens, then after refraction, all the rays tend to get converged at a particular point on the principal axis. They tend to get converged at a particular point on the principal axis. This point is known as principal focus. This point F is known as principal focus, and this is known as the focal length. F, it stands for the focal length. So the distance between the optical center and the principal focus is known as the focal length. Here one thing I must mention, students, in the case of mirror, what was the relationship between the focal length and radius of curvature? It was F equals to R by 2. That is valid in the case of mirrors, not in the case of lenses. So this point F might be anywhere, right? Because F equals to R by 2, that is the valid relationship only in case of spherical mirrors, only in case of mirrors. In case of lenses, no such relationship exists between them. There exists some relation, but that we'll discuss later on. That is some entirely different relation, right? So in case of lens, This is focus. So now we have understood why convex lens is also known as a converging lens, because it converges the rays to a particular point, right? So again I must repeat, a question may be asked like, why convex lens is also known as a converging lens? Explain your answer with the help of a ray diagram. In such a case, you are supposed to draw this particular diagram, right? So what we have understood from this diagram is that when rays parallel to the principal axis are incident on a convex lens, then the rays after refraction tend to get converged at a particular point on the principal axis. And that particular point on the principal axis is known as principal focus, right? Now since this lens is converging a parallel beam of light to a particular point on the principal axis, that is the reason why convex lens is also known as a converging lens, right? Now let's discuss concave lens. Concave lens, students, it is also known as a diverging lens. So let's check it out. Okay, this is a concave lens. You are aware, a concave lens is thin at the center while it is thick at the edges. Now draw a reference line. This can be considered to be the optical center, point 2. Now this is the first surface, this is the second curved surface. It's a part of a sphere. So its center would be somewhere over here. This is suppose C1. This is another part of a sphere. So its center would lie somewhere over here. All will have the same line. So the line joining C1 and C2, the line joining C1 and C2 would be known as the principal axis. So this is the line. This is the principal axis. Right? Now here what we'll do is, again I have told you, actually the refraction will take place at two places, at each of these two surfaces. But since the lens is constructed thin, so we will show the bending of light only from this reference line. Right? So let us consider a parallel beam of light to get incident on this concave lens. Now as I have told you, optical center is that point which lies inside the lens, from where if the light passes it will remain undeviated. Always remember, from the optical center if the incident light passes then it will remain undeviated. Now in this case what happens is, the rays after refraction, it will diverge. That is, it will appear to be coming from a particular point. Like this, it will diverge like this. So it is diverging. If you produce these in the backward direction, so all these rays will appear to be coming from a particular point on the principal axis. Like this. So this particular point from where the rays appear to be coming, this point, it is known as the principal focus. And student, this distance between the optical center and the principal focus, that is known as the focal length. So students, how to convince the examiner that concave lens is also known as a diverging lens? You need to first draw this ray diagram. This is absolutely mandatory. And then you need to convince what you conclude from this ray diagram. From the ray diagram, it can be concluded that when a parallel beam of light or when rays parallel to the principal axis are incident on a concave lens, then the rays after suffering refraction appears to be coming from a particular point. This is the real direction of the rays. But if it is produced in the backward direction, then the refracted rays appears to be coming from a particular point. Here, the rays are converging at a particular point, and here it is appearing as if these rays are emerging from a particular point, diverging from a particular point. So this is the reason why concave lens is also known as a diverging lens. So I hope it's pretty clear. One more thing, students. Basic difference, as I told you, it is converging nature, it is of diverging nature. Second difference, it is thick at the center while it is thin at the center. It is thin at the edge while it is thick at the edges. Another difference, its focus is real. Its focus is real. Its focus is real. While on the other hand here, the dotted lines are getting intersected at a particular point. So dotted lines, intersection of dotted lines is imaginary or virtual.
So students, that's it for this particular session. Hope you have understood all the topics which have been taught to you.